this video we will solve the remaining questions of GATE 2024 ACA. So before solving the question, let us say we don't have this connection and output is here. So this is a differential to single-ended operational amplifier. So first we'll determine signs of the terminals, whether this is positive or negative. We have to find out. To find this, what I will do is I will increase this node potential. If this node potential goes up, this is a simple CS amplifier, so this node potential will go down. If this node potential goes down, this will also go down. Again, here also it is a PMOS CS amplifier, so this potential will come up. So this is positive terminal and this is negative terminal. In the question they have connected negative terminal of the op-amp to the output, so it will look like this. This is a buffer. So if the gain was infinity, V0 by Vin will be 1, but here the gain is 40. So this node potential is V0. Vin minus V0 into A is V0. So Vin into A is V0 times 1 plus A. So the closed loop gain is A by 1 plus A0, which is 40 by 41, 0.9756. So the answer is B. In this question they have asked the small signal gain. This is a very simple question. For this we'll draw an analogy to solve this. Let us say I have RS here, some capacitor and R1, and if this network was not there, simply RD is there. If I apply input here, the gain from here to here is minus GMRD, simple CS amplifier. If I apply VI here for small signal, this node potential, let us say this is Vx will be voltage division between these two. For AC, capacitor will be shorted, so Vx will be R1 by Rs plus R1 into Vi. So the gain will be divided by this factor, multiplied by this factor. So the modified gain will become minus GMRD times R1 by Rs plus R1, because the gate potential is decreased by multiplied by this factor R1 by Rs plus R1. Similarly, here we can see, we know that the impedance seen from here is 1 by GM1, and RB and 1 by GM1 are in series. So this will be Rs RB plus 1 by GM1 and CS stage V out RD, this is Vi. So the normal gain is GM2 RD, and it will be multiplied by a factor of RB plus 1 by GM1 by Rs plus RB plus 1 by GM1. So the answer is option there has to be a negative sign. Minus GM2 RB plus 1 by GM1 by RB plus 1 by GM1 plus RS. That will be option D, I think. So there has to be a negative sign. So the other question is based upon zener diode. The capacitor is initially charged to 10 volts, and we have to find out the energy dissipated by the zener diode. It is given that zener voltage is 5 volts. So what will happen here is, initially the capacitor will be at 10 volts. When the switch is on, current starts to flow. As the current flows, the capacitor voltage will decrease. Initially zener diode will be on as 5 volts. Vc of t, initially this is 10 volts. The resistor value is 10 kilo ohm. So initially 0.5 milliamps current will flow. As time increases, this node potential will decrease, so the voltage drop across this resistor will decrease. So I will also decrease, current flowing will also decrease. When this capacitor voltage reaches 5 volts, the current will be 0. I will be 0 because the zener diode will turn off. If Vc of t is less than 5 volts. So the initial current is 10 minus 5 by 10k, 0.5 milliamps. The time constant of the circuit is RC. Tau is equals to RC, that is 100 milli. From simple first order RC circuits, we know that IC of t is IC of infinity plus IC of 0 minus IC of infinity into e power minus t by tau. If we put the values, it will come out to be 0.5 milli e power minus t by 0.1. The power across Z is zener diode is Vz into Iz of t, which is Ic of t. So it will come out to be 2.5 milli e power minus t by 0.1 milli. Vz is 5 volts. 5 into 0.5, 2.5 milli. The energy dissipated is integral of power. So it will be 2.5 milli integral e power minus t by 0.1 dt. If we simplify this will come out to be 0.25 millijoules. Here it is asked to find the small signal input impedance. The small signal equivalent of MOSFET is GMVGS. This is drain, this is source. Let us say the source potential is Vx. No current will flow in the gate, this is 0 amps. ID is Vt minus Vx into SC1. If we apply KCL at Vx, the current flowing in this direction is Vx minus Vt into SC1, and this current is Vx into SCL, and the current flowing in this direction is minus GMVGS. If we group the terms and simplify this, it will come out to be Vx will come out to be Vt into Sc1 plus Gm by Sc1 plus Scl plus Gm, and we know that It is Vt minus Vx into Sc1. If we put the values here and simplify, we'll get Vt by It as Sc1 plus Scl plus Gm by S square C1 Cl. If I divide each term with S square C1 Cl, first term will be 1 by j omega Cl, second term will be 1 by j omega C1, the third term will be minus Gm by omega square C1 Cl. So the answer is option B. And in this question, a n:1 step down transformer is given. The diodes are ideal diodes, that is V gamma is 0, no drop across diode, and Vs of t is given as 10 sin omega t, and it is given that the average voltage at output is 2.5 by pi. In the positive half cycle, the diode D1 will conduct. Since it is step down transformer by N, here if the voltage is Vs, the voltage across this node potentials is Vs by N. Similarly, here also it will be Vs by N. In the positive half cycle, this will look like this. This plus this minus Vs by N. VL of t is Vs by N. In the negative half cycle, VL of t will be minus Vs by N. In the negative half cycle, the value of Vs will be negative, so it will be Vs by N. It will be a full wave rectifier. So for full wave rectifier, V average is Vm by pi. So it is given that output average voltage is already 2.5 by pi. So the output voltage here is Vs by N by pi. So N will come out to be 4. That's it. Thank you.